Well, it looks like we can start. Welcome back, everyone. We're now on week number 12. So after this week is over, we are crossing the 75% mark for the entire semester. And the bigger announcement of the day is our exam three is now completely filled out. The coverage, the review information formula sheet, and two versions of the sample exam exercises. And also on Monday morning, I sent out the reminder to schedule your exam and the link for your particular testing center. So if you haven't seen that message yet, you can find it in the Canvas inbox system, or it also bounces another email to your ISU email address. Well, before we get started today, any questions or comments at the moment? Okay, well, talking a little bit more about exam three, as far as the scheduling goes, it's open to be scheduled between the dates of, I believe I opened it up for 13th if you want to test a little bit early. The 14th is going to be the official day of the exam, so we won't hold class on that particular day. And it can be taken as late as Thursday, the 16th as well. We will hold class on the 16th. And so if you do schedule on the 16th around exam time, then you could always go back to watch the recorded lecture. But pretty much we're just redoing the same kind of pattern that we did on exam one, two, and three. There'll be these particular sections, and the homework exercises are supposed to be very, very informative for what kind of problems, the level of difficulty that you can see on the real exam. So getting caught up on these sections is a great first strategy for preparing for the exam. After you're caught up and caught up on all those homeworks and starting to work through the sample exams, keep in mind this will be the real last page on the exam three. So this will tell you what information is provided and what kind of information you'll need to have memorized for the purpose of the exam. Well, aside from the exam, we'll talk a little bit more about it on our next class on Thursday. Next thing we have going on is assignment 5.3. This one's on strong induction, is due today, and we're starting off the section 7.3. I think we did actually start it a little bit. We did one problem, approximating the number of primes. And so we're going to talk a little bit more about primes, but our major discussion is going to be relative primality or relative prime integers. We'll loop that in with the extended Euclidean algorithm, and that gets us set up for finding inverse mod m in a particular algebraic structure. So pretty much everything we're doing in 7.3 is to get us set up to extending this list of properties so we can talk about division, or in this algebraic structure, we'll call it a multiplicative inverse. But any questions so far, folks, before we get started once again in 7.3? Okay, well, let's jump in. We were looking at a particular theorem that approximates the number of primes in a particular range. We have a function called primes n that's going to denote the number of primes less than or equal to any potential integer n that we specify. And finding an exact formula for this is a really humongous open question, a tough topic, but there's lots of nice approximations like this one down below. It says as the number n gets larger and larger as the limit tends towards infinity, the ratio between the number of primes less than or equal to n and this function, n divided by the natural log of n, is exactly 1. And talking a little bit more about the calculus in that, you can show, we mentioned using L'Hopital's rule, that limit, just the denominator, does in fact go to infinity because natural log n grows very, very slowly relative to even the degree 1 linear function. So this tells us altogether that we expect there to be infinitely many prime numbers. So that function we calculated once, and we said if n is 1,000,000, then primes n tells us we're expecting approximately, this is not dead on exact, the approximation gets better and better as n gets larger, it'll be approximately 72,382 prime numbers. So all we really did was we plugged in 1,000,000 in this form, but I think it's a little bit more effective to just use exponential notation, call that 10 power 6. We went to a calculator. This one will do the job for us. computed 10 power 6 here, divide by log. This one returns the natural log, 10 power 6. And that's where we got that number. We rounded to the nearest whole integer. Well, any questions at all, folks, with the recap on this prime number theorem? Okay, again, the main topic in this section is really about relative primality, but it makes sense to talk a little bit about prime numbers themselves before going into that specialized subtopic. The next part B is a little bit more vague of a question. Here we know that there's about 72,000 primes less than or equal to 1,000,000. But now we're trying to approximate how many 13-digit prime numbers are there. We're not computing the primes, we're not finding them. We're just wondering approximately how many would there be if we did try to count them all. But we can use this function once again to make this happen, primes n. When we say 13-digit prime numbers, the trouble is if we use primes n right away to get started, it's going to include 12-digit prime numbers, 10-digit prime numbers, all the way down to the prime number 2, just one digit, the minimal prime. So we have to actually use primes twice. Let's start with the largest 12-digit number whatsoever. The largest 12-digit number is, well, we could go 999, 999, 999, and there it is. It's 12 digits. We can't go one higher, or we're now at 13 digits. That's kind of an inconvenient number to throw in a calculator, but you can put that in a numerator here and a denominator here. But let's make one small approximation. This number is certainly approximately equal to 10 to the power 12. Kind of following the same values right here. If we use 10 power 12, the error is so small, then when we go to use primes n, we're going to be rounding to the same digit. So we now know the largest 12-digit prime number. So if we calculate to primes n on the largest 13-digit prime number, and on the largest 12-digit prime number with that approximation there, all we have to do is compute the difference, and we'll find the number of approximate 13-digit prime numbers. So let's start here. Let's find out how many prime numbers are at 12 digits. We can say primes. Let's give this a label. Let n equal that 10 power 12, then primes n is going to be equal to approximately 10 power 12 divided by that structure right there, 10 power 12, or excuse me, that's the numerator here, 10 power 12 divided by the natural log of 10 power 12. I was going to put that whole thing in the denominator once again. I was looking at that kind of sideways. So we'll throw that into the calculator, get another approximation here. Wrong tab, let me try again. So this is 10 power 12 divided by log 10 power 12. And so this is approximating the number of 12-digit prime numbers altogether. Comes out as a pretty large figure. There's quite a bit of them, so let's put this down on paper. Let's see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's start with 36, 191, 206, 825. So we have a value there, and we probably could have skipped this step and put just everything into the calculator, but we're just breaking down this computation to show the logic. So now we can use primes n on the largest 13-digit prime number, subtract this value from it, and that will answer the question altogether. How many 13-digit prime numbers are there approximately? Well, let's go off to the next level, the largest. 13-digit number takes a minute to write this down, just add one more digit to this one. So 9, 1, 2, 3. That was supposed to be a comma. Let me try again. 4, 5, 6. Hang on. My brain kind of conflated things. 7, 8, 9, 10, 11, 12 of them. There they are. Once again, let's just do a fast approximation here. This is approximately equal to 10 to the power 13. We could have just jumped to that, but this is the logic. This is the actual exact largest 13-digit prime number. We're just putting an approximation down here, and now we can say let m be equal to 10 power 13. Rewrite this step, primes m is going to be approximately equal to 10 to the power 13 divided by the natural logarithm, 10 to the power 13. Then probably quite a bit bigger than this value right here. Let's see how much it goes up by, just changing the order of magnitude by 1, going up to 13. So if we rerun this, this will be 10 power 13 divided by natural logarithm of 10 to the power 13. And it has one additional digit. So let's copy this in carefully, quite a lot of these. So 334072. Then 678387. So that's how many prime numbers are less than or equal to the largest 13 prime number. Now all we have to do is subtract this value here from this value to get all of the approximation for all 13 prime numbers exclusively. Bill, any last questions or thoughts, folks, with the layout of the process so far?
Yeah, so in my other classes, we've been doing a lot of step-by-step approximation. So for our like the primes of n, we would have done 3.6 times 10 to the uh, like just done that as an approximation right there. But for the purposes of this class, I'm assuming it would be better to save those approximations till the very end.
Yeah, I would say so. You mean at the very end, once we get the difference between this number and this number?
Yeah, and even beyond that, it'd just be like rounding to the nearest decimal.
Yeah, that would be just fine if you saved any kind of approximation like that. Other questions at the moment? Okay, well, to put this all together, again, really just using and abusing the prime numbers theorem repeatedly on both part A and part B, we can now make an ultimate conclusion that says the approximate number of 13-digit prime numbers is, and again, we could have just jumped down to this line right here, but this is just breaking down the computation, thinking about the prime number theorem here a little bit more on each level. So kind of a recap, but it's going to just be primes m, subtract from that primes n. So we're just forming the difference of this large number minus this number right here. It's faster to just do this in the calculator in this kind of format. So for primes n, we're going to take the same structure here, 10 power 13, divide by natural log 10 power 13. Subtract from that, this one, 10 power 12, divide by log. Again, this one outputs the natural log as its default, 10 power 12. And here's our difference. Still a large figure because, once again, this is quite small in terms of this value, going up one order of magnitude. So carefully putting this all in, it looks like this program is rounding to the nearest whole number at every single step. We have 297,881. Then next, 471,562. So quite a lot of prime numbers altogether. This one is a little bit tedious because this is a 13-digit prime number. I think I kept it a little bit smaller in the actual homework assignment for 7.3. But any last questions or comments at all, folks, with any of these computations? Okay, well, it's a nice theorem. It has lots of ramifications, gives us some decent approximations. They get better and better again as n gets larger and larger because of the limit structure there. But the unsatisfying thing about these prime numbers is what we really would like to do in many applications is find the prime numbers. We would like to find very, very large, gigantic prime numbers in high order of magnitudes, say 60-digit prime numbers and so on. This doesn't help us compute any of them. And so we're going to look into one computational method for actually computing prime numbers, which is horribly inefficient. It's not a great way to do this if you want to find large amounts of large prime numbers, but it's our way to get started to think about how would you compute a prime number. So one really ancient method is the so-called sieve of Eratosthenes. So this one's an algorithm just much like the mod and div algorithm we had right here that gave us the modulus of numbers and the floor of numbers. We traced this one out before. The author wrote it down in a particular way, and we just expanded it here so it could actually run. This algorithm is a little bit different. It's just given verbally, yet we're still going to trace it out. So it's a different kind of trace, but very similar in spirit. And a really decent coding challenge, if you had the time and you're really curious, is actually implement this as pseudocode, or even go beyond, implement it into a coding language of your choice, and run the sieve. Lots of different ways to kind of implement this. You could go with a for loop, you could go with the vectorization method. But here we're just going to focus on how did people compute these prime numbers to begin with using this method. We're going to also use this theorem that has two parts. The first part we've already hinted at. There are infinitely many prime numbers. And hey, a fun thought, we could have proven this in chapter 4 if we had the time to stay in chapter 4 longer. That's a proof by contradiction method. You can say, assume there are finitely many prime numbers, and you will derive a contradiction, which proves there are infinitely many. So that's an interesting proof all on its own. And this theorem is also helpful as well in using the sieve of Eratosthenes. It says if we know that a number is composite, meaning there is a factor of that number other than itself and one, then a composite number will be divisible by some factor that's less than or equal to the square root of that number. So we're going to use that fact together with the sieve of Eratosthenes to find all prime numbers less than or equal to 40. 40 just so that we're not here all day running through it. Well, first let's look at what the sieve does. The sieve of Eratosthenes returns a list of prime numbers up to a given integer n. Ours will be 40, and the way it does it is it creates a list of candidate primes. So here's our list right here, starting at 2. We know that's a prime, but we're thinking of it as a candidate as we begin, and repeatedly marking the first unmarked prime number as prime. That one is definitely prime, so the first number there becomes prime. And striking out all entries in the list that are multiples of that number, or in other words, you can start with 2, and any number in that list, mod 2 that comes out as 0, is a multiple, and it gets struck out. So that's the sieve of Eratosthenes. This can be applied directly in a computer programming system, but again, it's not efficient to try to find out the exact number of these primes here. That would be code that would run days or weeks or maybe not finish at all. We have to be more effective to try to find all those prime numbers. Well, we'll give that sieve a try by tracing it out to just see how this runs. But any questions at the moment before we get started? Okay, after this topic, we're going to then look into the topics on relative primality and get into the extended Euclidean algorithm. But let's start this out. If this one comes up as an exam question, I think I would do this step right here where it's just printed out the list of integers, because this is a bit tedious now thinking about it. But let's carefully write out our list. 2, 3, 4, 5, 6, 7, 8, 9, 10. Then let's just drop a row, keep these organized. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So riveting stuff. Again, on a real exam question, if this is on exam 3 or the final exam, I'll just print this out so that we can save some time writing this. So next, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, and finally, here's 40. So there's our list right here. We're going to first mark this one as being prime number. That's convenient. The first number in the list is in fact prime, so we're on our way with that. That's an honest step to take. Then here's what the next part of the algorithm does. It will repeatedly mark the first number as prime and strike out all entries in this list that are a multiple of that number here. So 4 is a multiple of 2, or 4 mod 2 is 0, said an entirely different way, but an equivalent way. So that means this is struck out. 4 we know is not a prime number, so that's the right step to take. We're trying to convert this list that's provided into a list only containing primes. So we go down the list. 6 mod 2 is 0, so that gets stricken out. And same with every even integer. So we've really just kind of annihilated the list at this stage. Let's wipe out all the evens. Every one of these is a multiple of 2. And so now we have 1 prime down for sure. Any questions at all, folks, with that first step? Okay, so we indexed the first one, marked it as prime. Now we increment the index. Anything that's not struck through is now automatically designated as prime. And you have to wonder, would that always be true? But that's the role of this part of the above theorem right here. When we look into the number 3, if we didn't know if it's prime, we can consider maybe it's composite. If 3 is composite, it'll be divisible by some factor less than or equal to square root of 3. But the square root of 3 is 1.7, smaller than anything in this list right here. So that means it is not composite. It's not divisible by anything prior in the list. So we automatically mark it prime. I mean, we definitely know 3 is prime, but if this was a large list, say up to 200, this becomes a valid thought you might want to say. Why do we know for sure that when we increment by one integer from index 1 to index 2, is this guaranteed to be prime? This part of the theorem makes that the guarantee. Once we go to that next value designated as prime, we repeat this step right here. Anything that's a multiple of 3, or anything mod 3 that comes out as 0, is struck out. That means it's going to be a factor of 3, which means it's composite. So we skip all the way here. 6 is a multiple, but it was already stricken out. But so is 9. Then we move over. 12 is the next multiple. After that is 15. Strike that one out. 18 is already gone. The next multiple is 21, so we eliminate that one. The list is really getting wiped out pretty fast just at these first 2 steps. Then the next multiple is 24, which is gone. 27, 3 divides there, going in 9 times. 30 is already wiped out. 32 is already eliminated. The next one after that, 36. Sorry, I lost. Hang
33.
on. Thank you, 33. I was going by threes, but then I realized lost track. From 30, go to 33. Thanks for the help on that one. 33 is the next multiple, then 36, stricken out. Then finally, 39 is also a multiple of 3. So we're done up to that list. 5 is the next value. We definitely know that to be prime. The theorem highlighted guarantees it. So we designate that as a prime, and at this stage, there's not much more to do, right? There's still stuff to cross out. For example, we skip through 10, 15, 20. But 25, mod 5 is 0, so it's a multiple of 5. Eliminate that one. 30 is gone, but 35 is still remaining. It must get eliminated. And 40 has been eliminated as well already. So we move up to 7. 7 is designated as absolutely being prime at this stage using the algorithm. And if we look through the list, there might be something left here. Let's take a look. Multiples of 7 are 14, 21, 28, 35. Nothing left to do. We just designate that as a prime and then increment. You know, the challenge of writing down the sieve of Aristophanes, if you're not using a for loop, is you have to recreate the list every time you strike things through. So you're constantly refining the original list of candidates every time you increment from one to the very next. So when we increment again, our new list only contains 11. 11 we certainly know is prime. Multiples would be 22, 33. And beyond that, we are exceeding 40. They're already gone. So we go up to 13. Multiples of 13 are itself 29. Hey, so excuse me, not 29, 26, and then 39. Then go off to the next. 17. And again, if we're at any stage unsure if that's prime or not, it definitely is. But we could go back here, take the square root of 17. If that's a composite number, there's going to be a factor d less than or equal to 4. Once we take that square root, we're only using integer values. But 4 doesn't divide 17, 3 doesn't, 2 certainly doesn't. So it's automatically prime by the highlighted theorem. Same idea with the 19 here.
So you've only been showing that theorem with prime numbers. Can you show it with a composite number? Because I'm trying to understand how that kind of works.
Yeah, that's a great thought. So if we say, look at, say, the 18, this one was already crossed out, but it's crossed out because it was supposed to be composite. And this theorem, yeah, we're only showing when it fails to hold. Let's show it when it really holds. That's a great thought there. We take the square root of 18. Square root of 18 is 4.24. That means we know it to be composite, and the theorem above guarantees there will be some factor, call it d, less than or equal to 4, because it has to be an integer. So something less than or equal to 4 will divide 18, and 4 works, and both 2. If we looked at a higher value, say maybe 38, square root 38, this tells us numbers must divide it. It could be 6, 5, 4, 3, or 2. There's got to be just at least one in that list, which will divide 38. Does that make sense with the run through with this theorem for values that actually work?
Kind of. So basically, what this does is gives a upper limit of numbers that can be candidates as divisible, and then you just go through that until you find a number that divides it.
Yeah, exactly. And what's tricky about it is giving an upper limit. Say when we did the square root of 18, upper limit for the possible candidate of divisors was 4 on that one. But we know 9 also divides it. So it doesn't give you all the divisors. It just says there will be one at least divisor less than or equal to the square root, guaranteed. There could be many more greater than that square root. Does that make sense there?
Yeah, thank you.
You bet. And thanks for that question there. Just looking at this theorem again, it's a pretty interesting one. The author does give a nice proof of it. The proof is pretty tricky in the reading. And that's pretty much its use is we're using it directly to validate that when we're circling these primes, they are in fact primes, but it has other great uses as well. Other questions at the moment? Okay, well, we're pretty much through the list. And when we get to these last values, the higher multiples of these, more higher than multiple 1, are beyond 40. So when we circle 23, there's nothing further that can be canceled out to the right. And pretty much everything here that's not canceled out is automatically designated to be a true prime number. So 29 is prime, 31 is prime, all the way up to 37 is prime. And if for some reason civilization completely collapses, but you still have a chalkboard, you want to find all prime numbers less than, say, 200, this is pretty efficient. This is a great way to find those prime numbers without working too hard. So it's a great algorithm in that sense. But again, we really only did this algorithm to just think a little bit more about primes before getting into relative primality topic and just show ways of computing primes through this algorithm. Any last questions at all, folks, going through this one? Okay, it's also a weird trace, right? Because the algorithm isn't provided using pseudocode whatsoever. It's just provided in ordinary words. It tells you what the steps should be in ordinary language. And this is what we got. So again, if you like to give this a try, you could implement this. Here's the sieve of Eratosthenes. I put down some syntax here for how it should go. You could use this in your homework if you like, just as a double check when you run through this problem. And here's what it would look like. It's a pretty tricky little function. So there's other ways to implement this, but we went to the vectorization approach on this one. We start with a list that goes from 2 through n. This is the list of primes. That's what this whole thing was right here. Then we start at the index 1. Let's see, where is that mentioned? Can create a list of primes, repeatedly marking the first unmarked number as prime. That's what we did here. We indexed as 1 to say that's going to be our very first prime. Then the while loop is essentially doing exactly what we did by hand. Tracking through it, we say P is going to be P list, bracket index is saying, I'm going into this list, designating P as the prime 2. Then this is essentially one big filter. We're going to cross out all multiples of that prime. So while this P list is less than or equal to P, so while we're somewhere inside this list, not going down 40, if the mod is not 0, then we keep that new value. This updates the list altogether, and then it just, this part right here, just tells us how to increment from the next one off to the next. So if you run something like this and say sieve 40, really, we just did the same exact thing we did here. All of these are the primes listed out. And you could do other fun things like, say, sieve 200 actually runs kind of efficiently. But you'll notice the moment you try to do something like sieve 1000, here's where it's going to eventually start to struggle. Well, it didn't struggle too hard. I think this computer's a little bit faster than my home one, potentially. How about one more 0? Yeah, it actually did it efficiently. It reached the max print on this one. Eventually, though, if you give this function too high of a value, higher order of magnitude, we're never getting into even the 12-digit numbers. This is going to probably take too long to run or just hang up, reach an overflow or some kind. But it's a fun little algorithm. Again, this was our way just to think about how to compute primes. You could implement this in a lot of different kinds of ways. But really, this was kind of a warm-up for our ultimate objective in this section, getting to the extended Euclidean algorithm. This one is what's going to allow us to extend on this list here, by allowing us to give a type of division, multiplication by an inverse, and in some weird way, greatest common divisors are how you divide or give a multiplicative inverse mod n. So this is going to be our objective, our major target next, a new trace. And we're going to extend to not just primes, but now the concept of relative prime numbers. So we'll say two numbers, two integers, n and m, are relatively prime if their greatest common divisor or greatest common factor is exactly 1. If 1 is the largest number that divides both n and m. They could both be composite numbers, but they'll be relatively prime as soon as their greatest common divisor is exactly 1. Well,
If their
that,
factor trees are completely different, is another way of saying that.
yeah, absolutely. That's a great way to say it. If we look into factor trees of, say, both of these right here, there is no common value other than 1, but we really wouldn't put that in a factor tree typically. Other questions so far?
Okay, I just have a quick thing to be pedantic about the code above.
Yeah,
Uh,
or this one right here, or
no, above in the, yeah, in this one. Um,
yeah,
I just want to point out that this is using division, which takes a lot more um, computation cycles. So if we were given to optimize this, if we were given that finite maximum size, it can be optimized quite a bit to build an array and then start deleting entries of multiples instead of going through every single index. And I
yeah. This
mentioned that it
optimized a
can be
lot.
optimized, but uh, I figured this is a prerequisite for some computer science classes, so I figured I'd want to mention that.
Yeah, thanks for mentioning it. So it could be optimized in that kind of sense as well. Also, if you looped in this topic right here, if you insert that concept into this algorithm here, you can also optimize it a little bit further. Same kind of idea as you're saying. This is going through the entire index list, but actually it could stop when it runs through some of these values using this theorem as well. So yeah, it could be optimized in a lot of interesting kind of ways. Other questions about it or comments? Okay, yeah, thanks for mentioning that. This one is pretty crudely put together. It was pretty challenging for me, and I had to use a logical OR and a modulus inside of here as well with a logical not at the same time. So it's a pretty tricky one to put together. I think if you're doing this for the first time from scratch, the for loop might be easier to put together. But again, like you're saying, maybe not as efficient as trying to vectorize it in this kind of way. But let's take a look into this idea once again. And I like the comment you made about the factor tree. So it says determine if the pairs of integers are relatively prime using the Euclidean algorithm, the same algorithm in section 7.2. But when you go to do this as, say, a homework problem, I don't care how you do this. So if you did this by hand, that'd be just fine as well. If you trace the Euclidean algorithm by hand, that'd be fine. And if you decide to implement the Euclidean algorithm, here it is, and just run it in a computer system, whether it's R, C++, and so on, that'd be a fine way to do this homework exercise as well. So I'm going to leave it completely up to you how you'd want to calculate these. We'll start with the factor tree idea because that gives us a good way to think about relatively prime. We take 255. 5 is certainly going to divide that. It's going to go inside there 51 times. And well, what about 51? 3 would divide that. 3 would go in there. I believe that's 17 times, but let me double check my arithmetic on this. 5 times 3 times 17, yeah, it gives us our 255. Then when we go to look at the 377, well, something's got to divide this, or it's a prime number. You know, we could look into C, 377 It's not on the list. So 377's composite, something will divide it. 2 doesn't divide. 3 doesn't divide. 377 divided by 3 gives us a non-integer value. If we take the square root of 377, we know we only have to check candidates up to 19 to find a divisor. So take 377, 4 won't divide since 2 didn't. 5 certainly doesn't divide, 6 won't because neither did 2 or 3. What about 7? Oh, no luck on that. 8 won't divide, 9 won't because 3 didn't. How about 11? No luck there. Let's keep on searching. 13, and we've got a hit. 13 goes into 377 29 times. And if we look into our C, is 29 on the list? It is, it's prime. So that means we're done. That's our factor tree. No factors whatsoever in common. Well, that means the factor 1 is in common, the greatest common divisor of 255, 377 equals 1. So 255, 377 are relatively prime. So we've got relative primality on those two there. So again, that's one way to run these kind of problems. We could do the same thing in part B, but let's cheat a little bit on this one. I mean, not exactly cheat. Let's use the Euclidean algorithm, this one right here, because it gives us the greatest common divisor right away. Tracing it takes a while. The factor tree is probably a little bit faster. So we're just going to run the pseudocode. Any questions before we try it out on part B? Okay, so we've got 2 large integers, and on visual inspection, I can't tell if anything divides both. You might have already seen something, especially if you're checking with calculators or just really, really good at mental arithmetic. But if we use the Euclidean algorithm, this is a pretty fast process. It's a recursive process that we've traced to show how it works, and it absolutely gives us the greatest common divisor. So here's that pseudocode implemented into R. Cite or call G Euclid 510 697 returns a value of 17, which tells us 17 absolutely divides 510. We want numerical evidence. Here it is, goes in 30 times. 17 will divide 697. Definitely works. And so this gives us immediately and really effectively the greatest common divisor, 17. So we can say Euclid 510 697. So here we're using the Euclidean algorithm from the prior section. This gives the greatest common divisor of 510 697. Which came out as 17. That means 17 divides both, and so 510, 697 are not relatively prime. In other words, if we worked really hard at the factor tree, like we did here, we would see 17 branching on the first integer and somewhere branching on the second integer. Well, doesn't mean there's anything wrong with the numbers, but when the numbers are relatively prime, it's going to give us something extra. This is one core ingredient for, again, our ultimate objective, finding an inverse mod n. Any questions so far, folks, about relative primality as a topic? Okay, next, we're going to look into a really interesting result in number theory. Our author calls it a lemma, but it's in my opinion, a nice theorem in its own right. A lemma is a way to say we have a mathematical fact that's just going to be used once in the textbook elsewhere. The way this lemma is going to be used is constructing an inverse mod n in the very next section. The lemma says there are multiples of n, think of that as, say, the n, and m, think of that as an m, that add up to the greatest common divisor of n and m. So there are some multiples of these numbers, some positive, some negative, that we're going to add up to 17. There will exist some values that can solve this. So if n and m are any positive integers, we'll designate r. I think that's a weird choice, but to keep the things the same in the reading, I'm keeping it r just like in our textbook. R is going to be the greatest common divisor of n and m. And we will find integers, these are the multiples x and y, multiplying n, multiplying m, resulting in r. So this is going to be the core step in giving us a new algorithm, inverting mod n. We've been mentioning that our ultimate goal is to invert to mod n because I feel like otherwise all these collections of facts seem random, but there is an ultimate objective of what we're trying to get to with the extended Euclidean algorithm. This is going to be cited directly to extend this list to inversion. Well, there it is. We're going to trace this to see just exactly how it goes. On the right is the ordinary Euclidean algorithm, just for a quick reference. So what we're taking for the extended algorithm, a set of integers n and m. We want m to be the larger of the two. It's going to output an x, y, and r, which are the same as these x, y, r's that you see here in the above lemma. And once we have those outputs, x, y, and r, this is what it solves. So it's only going to return the x, y, and r, but the guarantee is we have found the multiples of both n and m, which add up to the greatest common divisor r. It's an interesting algorithm. It's not too different than this one that we traced in the last section. It's recursive, but when you do the recursion, you have to pause the execution until this executes, then you resume the execution and do a specific return. So this one's a little bit tricky. We'll take our time with it to see how it goes. It's a trace just like how we've traced mod and div, or how we've traced a for loop before when we're looking into summation notation. But this one is a little bit different. Any questions at all, folks, before we begin the trace? Okay, let's try this out. We're going to execute extend in Euclid to compute the greatest common divisor of n and m, find the integers x and y that solve this equation here for 7 and 24. So let's go carefully and methodically. Step 1, we call. I'll abbreviate this just to shorten up the writing to just ext for extended. Call extended Euclid. And we want to use n and m, where n is the smaller of the two, so 724. So that's the input n, the input m that goes inside. So we made our function call. Now we're going to trace the execution. First, we have to determine if we're going to execute the if block. And that'd be great because if we do, we're done. If the mod is 0, then x is going to be 1, y is going to be 0, and n itself is the greatest common divisor because n divided into m. So that's like the trivial case. If the mod is 0, then you're done. This equation holds just trivially right away. Doesn't happen here because when we go to take m mod n, we're taking 24 mod 7, and that's coming out as a 3. It's non-zero, so we don't hit this step here, which means we skip down to the else block. Else block runs. Run line 3, and now that it's running, we make a recursive function call. So on this recursive function call, we need to be really careful. It's going to return an x, y, and an r. And I think it helps to use subscripts on this one to just identify what the values are going to be. But let's write down in our trace, the else block runs, make a recursive function call and pause on line 5. We have to come back to this step right here. We need the values x, y, r before we can actually execute line 5. So this original call of Euclid, extended Euclid 724 is just waiting now as we do this function call. So I'm going to indent just to show how we're kind of descending down in the layers of recursion on this one. This will be our first recursion call, recursive call. This right here, extended Euclid, it's going to return these values. So I want to state that right away, just for the sake of organization. And because this is recursive call 1, let's call them x sub 1, y sub 1, r sub 1. You don't have to use subscripts, but I think it helps to track where everything is going. So these will be the values that get returned from extended Euclid. And let me keep my notation the same. The author is using hyphens, so I'll try to keep hyphens as well here. Extending Euclid. What's going in is m mod n. It's referring to the original m and n on the very first function call. So m mod n is 3. That goes inside. The value n right here is this n, same as we indicated at the very top, the 7. So we're making a recursive function call to Euclid 3.7, get the values x1, y1, r1, and once we have that, we'll go back to the original function call, resume line 5. So there's our next recursive function call. We're back at the top with a new n value, a new m value, and we have to trace through steps 1 through 5 once again. But any questions at all, folks, to this level? Okay, starting over from the very top. New function call means we're at this. We want to check if this block will execute. So we do m mod n again, but notice m and n have switched. Once we've made this function call, this is the new n, this is the new m to maintain that formatting. So we're taking this time 7 mod 3. Sadly, 7 mod 3 is 1. The remainder after division 3 to 7 is 1 itself. That means it's non-zero. This if block doesn't execute. Not 0, so the else block is going to run instead. Else block runs, which means we make a new recursive function call. Make a recursive function call and pause on line 5. So now we have 2 calls to extended Euclid. They're both hanging, waiting for return values on line 5. And so now we descend further into the next layer of the recursion. So new function call, new values x, y, r. We'll update the subscripts to x1, y2, r2. And here's call 3, recursive call, x2, y2, r2 will be defined to be the output to extended Euclidean once again. We have to be really careful with the input when we do that, because once again, the input is going to be m mod n, but that's this m mod n from the recursive call on this one. That mod came out as a 1, so a 1 will go here. And then when it says this n, it's referring to that 3 value there, or maybe if you put an n there, referring to that same exact 3 value there. So we're calling extended Euclidean on 1, 3 now. So that's our next function call. So that means we're, once again, at the very top. We're retracing this all the way again, starting at the if block. We'll check if this executes by doing m mod n once again. M mod n is going to be equal to, here's our new n value, our new m value on this function call specifically. And that's great because now that means you're taking 3 mod 1, but with integers, mod 1 is 0. But that means if block does execute, we've reached the very, very bottom of the recursion. This is the base. We'll say here, if block executes and returns the following. Now recall, we are calling extend Euclid on 1, 3 is going to store in x2, y2, r2 the output to that function call. But because the if block ran, here are the returned values. And our author's pseudocode is very, very terse, very briefly written. This is a list of 3 values. If we're saying this is defined to be a list of 3 values for the output of extended Euclidean, we're saying at the same time that x2 is now 1. So x2 becomes 1. That's supposed to be a comma. Let me try again. Likewise, for this value, y2, that's going to be defined to be as 0. And likewise, r2 will be defined as n, but we have to check which n we're referring to. We're inside this function call, n is 1. So we've got an x2, y2, r2 value all stored. The extended Euclid 1, 3 call is completely done. Remember, we paused on line 5 for 2 other function calls. So now we backtrack, we unwind the recursive calls, getting back to the original function call here. So one recursive call is done, we undo this one, and then we'll make a final return back at the very top. Any questions or comments so far, folks? Getting to just the bottom of the recursion down here. Okay, so now let's go backwards. We have to unpause here, return the values to get an x1, y1, r1, unpause here to get the original, or excuse me, the final return, which will be this combination here. That'll be the x, y, and r that we'll verify ourselves has better solved this equation right here at the top. So next step, let me just find a good spot to park this. Let's call this maybe step 4, but really we're just unwinding this recursion. So I'll kind of indent it to that level. Step 4, return to extended Euclid 3.7 and run line 5. So we're unpausing that line 5 on this one specific function call, 3.7. So that's going to be the n value, the m value. Let's take that off. We're on this line 5 now. And it has a very particular format to that function return. So again, this is just a list of 3 different values. The list says your first thing that's going to be your output, not the original x, but an output to x1 is formed through this part right here up to the comma. So let's define that as x1 is going to be defined to be equal to, when it says y, it's talking about the y right here, the y2, because we're returning to Euclid 1, 3, it was paused on line 5 on this recursive call. Going back to Euclid 3.7 means it has the x2, y2, r2 that's going to redefine x1, y1, r1. So x1, following this format, is going to be y2 minus the floor of m divided by n times x2. That's the first output. Let's just compute this through to get a value out. Y2 is stored as a 0. Minus the floor, when it says m divided by n, it's referring to these values. So the floor of 7, 3. That's just going to be the number of times 3 goes into 7. So that floor is exactly 2. Times x2, or x2 is a 1 value. So this is -2 times 1, or a -2 altogether. So now we've got an x1. x1 is -2, and then we just go to the next value of the output. The next output is going to be, remember it outputs x, y, r, so we'll label it as y2. Y2, by the output down below here, when we unpause line 5, is just an x value. But it's an x value that came from the recursion on Euclid 1.3. It's 1. And there's nothing more to that story. Y2 is whatever the x value happened to be. So that one's kind of nice. It's exactly done. Let's actually write out as a formula. Y2 is x2, coming out as a 1. So nearly there. Last part of this return should be r. Oh, hang on, let me fix my subscripts. That should have been a y1, not a y2. So we've got a y1 settled with the subscript fixed. It's the 1 value right here. Now we return to r1. It just says r. So nothing actually fancy with what happens with the greatest common divisor itself. Whatever r happened to be, it's going to stay the same. It's just being carried up as we unwind all the recursions, the same exact value. So R1 is defined to be R2, which was stored as a 1 on the step 3. So we've got values now for Euclid 3.7. Once we have values for Euclid 3.7, that's what we were hanging on this last pause. On the original function call at the very, very top, Euclid 7.24, we had a pause on line 5 right here as we fixed or finished the output for extended Euclid 3.7. We have that output. We have x1, y1, r1. They're all here. So now with those values, we make a final return. We're going back to the original function call, outputting our final xyz. Any questions with the algorithm so far? Okay, let's do this final return. This is now step 5. We're now returning to extended Euclid 7.24. Once we had the values for x1, y1, r1, this pause is done. So we go to line 5, run line 5. When we run line 5, let me just redefine. That's the new n, that's the new m value. But running line 5 just means we're redoing this all over again. So back to this function call. We're first going to define an x value. So we want an x value here, and the way x is defined is through that entire piece as a formula. Really, once we've done it once on step 4, same exact process on step 5. So x, let's call this, just to be fancy, this is our final return to indicate the process is now over at this step. X, our first return on the extended Euclid, will be defined to be equal to same exact format here. We'll go this time y1 minus the floor of m divided by n times x1. So we cite what the values were for y1 and x1 on step 4. So we have these values ready to go. That's what was given on step 1 when we did that recursive function call. So we have those values. Plug in y1, which is 1, minus the floor of m divided by n. In this case is 24 divided by 7. The floor of a division like that is just the quotient. 7 goes in 3 times. That's the exact floor on that one. Times the x1 value, which is -2. So this finally becomes equal to 1 minus 3, that's the floor, giving us a 3, times -2. And that will come out as a 7 altogether. So our final return, 1/3 of the way done. We get a 7 value, tracking from here to here following the color coding. But we also return a y value. The formula is just a lot more clean this time. Whatever y is defined to be, it's just going to be the prior x1 value, whatever it was. And the x1 value is right here, -2. So our y value is done. We have an output -2 altogether. And the final step is, again, nothing fancy. We're just carrying the value of 1 that came from right here up to the very top of when the recursion started, the original function call. So this r right here, our final part of the output, is defined to be r. But we're referring to r1 specifically. It just so happens it's still just a 1. So there are our 3 values altogether. And, well, that's pretty much the whole algorithm. In my opinion, it's a really, really tricky trace, probably the trickiest one we'll do all semester, because of how the code has to pause right here, do the recursion, and then feed an answer back, resuming that last 5 line. That's not something we've ever done before, so this is our first look into that kind of problem. Any last questions or comments at all, folks, running through that trace? Okay, took a while to get there, so one thing you should do, just because this is a fast check, is see if it makes sense. If the trace worked as intended, that equation here must hold. I'll focus on r equals xn plus ym. R is just defined to be the greatest common divisor. So r must be equal to x times n plus y times m. R in our problem is a 1, must be equal to 7 times n, and n was 7, plus y times, y is defined to be -2, times m, which is 24. So if the extended Euclidean algorithm worked as intended, that equation should be true. This is 49.
That needs to be a -2, not a 2.
Oh, thank you. That was freak out a little bit. This is not a fun one to try to find an error in, right? That's like combing through with a fine comb. It's almost easier to redo the whole thing than find a spot there. So thanks for spotting that. That should have been a -2. So this reads 49 minus 48. And yeah, that's exactly 1. So as far as the homework goes, I'll ask you to trace this. And this could be a final exam question, but it won't make it onto our exam 3, since exam 3 is going to end on section 7.2. Well, we did it, folks. If we want to implement this algorithm here, it's actually not too hard to write. It's way harder to trace, which is what makes it, again, pretty unusual. Here's the extended Euclidean algorithm altogether. We make a call here on mod and div. Bracket just says I want the modulus part, not the floor. If it's 0, we return 109. That's almost a verbatim writing of what we had right here. Else, we return the extended Euclidean use mod and div n. That's just a rewrite of this with the mod and div function from 7.2 the author provided. And the final return, this is the line 5, is these values here. X prime, Y prime, our result. And we combine it in this kind of format. Y prime minus the modulus times X prime. That's just this formula implemented. The second part of the output is X prime. That's just this right here. I called it X prime in the syntax. And R just matches with this R. So if we call this on 724, extended Euclid, 724, those are the return values. Just as before, we get 7, -2, and 1. You don't have to run this, but again, it's kind of fun to do in a way to try to see how to implement the pseudocode. And it's interesting in the sense that it's starting to stack a lot of our functions together. And we'll extend on this even further to give syntax and an algorithm for finding inverse mod n. Somehow, some way, this is the core ingredient to inverting mod n. Last part of the problem here, I didn't actually assign for the homework. It was more just to run the syntax once more. So if we run it for some more painful values to trace through, this trace would take quite a while, probably lots of paper. But the algorithm just rips right through that. The greatest common divisor, 254, 435, is 5. And it's an extended Euclidean algorithm because it also says the value for x is 16, the value for y is -9. Put these all together in a check just like on this one, and we found values that are multiples of n and m that return the greatest common divisor. So we can say here, x is 16, y equals, I forgot already, -9, r is 5. And a fast check on this one would be, take 16 times n, 245, plus -9, I forgot that negative sign again, -9 times m, 435. It had better be equal to 5 exactly. So let's verify that. 16 times 245 minus 9 times 435 does resolve to a 5 altogether. So we've got it, folks. This is kind of an interesting tour of number theory. It's skipping around a lot of interesting results. It's not calling this a major result, but for our purposes, it really is. In some books, this might be a theorem altogether. We're calling it a lemma, and this is the algorithm to execute that lemma, find the values x, y, and r, only because we're going to use that for one purpose. Find, say, the inverse of 8 mod 17, something like that. Finding an inverse modulus 17 is its own topic, so we're going to look into a new algebraic structure, loop in this algorithm, and show how to do inverses. With, again, the ultimate goal, extending this list to a part 5. Well, any last questions or thoughts, folks, before we call it a day? Okay, well, have a great afternoon, folks. When we come back on Thursday's class, we'll be looking into our last section on number theory before we go into the other topics, looking into relations and equivalence classes in Chapter 8. Here is where all of our algorithms, starting in 7.2, pretty much culminate. And so we'll see some pretty interesting results and applications to computer science at the same time in this one section. But have a great afternoon, folks. We'll be back to the next section on Thursday's class. Thanks. Have a good one, George. Thanks. And here's this back for you. See you later. Have a good one.